So the third and final speaker of the session is Marina Paez from the Universidad Federal de Rio de Janeiro. She's going to be talking about modeling with a large class of unimodal multivariate distributions.
Yes. Okay, thanks. So this is a joint work with Professor Stephen Walker. We worked on this at the University of Texas at Austin when I was visiting as a postdoctoral fellow. So in this presentation, firstly I'm going to introduce the problem, and then I'm going to introduce a new unimodal density for univariate data, and these distributions are going to be extended for the multivariate case. And finally I'm going to give an example with the Rio data set, which is the data set from Boston housing data set. In the introduction, I'm going to the motivation of this work is to work with the clustering problem. So in a clustering problem, the idea is that given observations x1 to xn, our objective would be to subdivide the sample into subsets. And the idea is that each subset will have to be similar in some way. So as this example here shows 1,000 points in the 2 dimensions. And clearly we can see that there are 3 different patterns, so probably 3 different clusters in there. So the idea would be that we're going to label which one of these observations with label 1, 2, or 3. This also is the same as assigning different partitions of the index set 1 to 1,000 into 3 disjoint sets. The traditional approach to model this kind of data is through mixture models. So the idea is that each component of the mixture would represent a parametric density, and so each one of those clusters will be represented by a parametric density. And then typically it would have a mixture of normals. So the model would be like a mixture model like that. We could have an infinite model like the one we are working with, or we could also have instead just a finite mixture. So normally, normal distributions would be used, and then the assumption here then would be that each cluster would be modeled through, or could be fit by, a model distribution. However, that's not always reasonable. We could have that a cluster, for example, could not be symmetrical, for example. You could have a skewed density or something like that. So to be able to fit a model like that, you wouldn't be able to do with a single normal. You would have to have more than one normal density to be able to fit this cluster. So that wouldn't be ideal, because ideally we would want one density for each one of our clusters. So to solve this problem, mixtures of broader and non-normal class of unimodal densities have been used for clustering in the univariate setting. So our motivation in this work would be to introduce a new class of unimodal densities, but that can be easily extended to a multivariate setting, because we notice a lack of work in 2 or higher dimensions for that kind of problem. In our work, we are going to model the marginal density functions using the Chin-Chin representation on the real line. I'm going to talk about that in a minute. And the dependency structure for the higher dimensions will be developed using a Gaussian copula model. So the representation of Chin-Chin states that any random variable with a unimodal distribution with the mode at 0 can be written as the product of x times z, where x would be uniform on the interval 0, 1, and z would be independent of x and would have an adequately chosen distribution. However, if we choose a natural density for z like the normal distribution, what happens is that the density of y at 0, which is the mode in that case, would be infinite. So, in fact, the density it needs to be somehow unusual to ensure that it won't be the case that it be infinite. So to solve this problem, instead of working y as the product of x and z, we write it as x over z, x divided by z. And for a mode different from 0, a kappa, for example, in the real line, we would write y is equal to kappa plus x over z. So the idea here, because we want a very flexible unimodal density, so ideally we wanted to cover every possible unimodal density on the real line, we want to pick a very flexible density for z. Ideally, we would want a density that covers all possible densities in the real line. So a mixture of normal distributions would be ideally for the specification of z. So we believe that if we specify z as being as flexible as we can, like having a full class of the densities, would have possibly a full class of the unimodal densities as well. So let me just go back. I'm going to show it here as I don't have anything to point. So the idea here is that this z here will be a mixture of normals, and then we'll have a very flexible unimodal density for y. Okay. So it's expedite to actually find the joint density of y and x when z is one single normal density. Okay. So if we specify z as one density with mean mu, normal density with mean mu and variance sigma square, the joint density of x and y will be given by this expression here. And as we are interested in the density of y, we can integrate x out, and after some algebra we get to this expression here, a closed expression for the density of y. Then our idea is that we're going to do a mixture of those densities that we found on the previous slide. So this would be our model, okay? We have a mixture of the densities that we found in the last slide. But we work with a different parameterization. Instead of work with mu and sigma square, we work with mu and c, where c is given by, just by here, mu over sigma square. So with this parameterization here, it's easier for us for identifiability concerns, because we are going to assume that this parameter c here is constant over the components, okay? Doing this constraint is similar to keeping the variance terms fixed for identifiability concerns in a mixture of normal model. Here's just an illustration. We have the density function of a mixture of two components, where the mode here is at 10, and we have then mu equal to -5 and 20, and the weights are 0.8 and 2. So that's just an example of a mixture. Well, to complete the model, we are going to specify some prior distributions for the parameters. So we have the mu's, the kappa, which is the mode, the c. Okay, the mu's and the kappa will give a normal distribution. For the c, we're going to give a gamma distribution. And the prior distribution for the weights will have a strict breaking construction, given that way, where the vj's are independent from a beta distribution with parameters 1 and m. So as a consequence, the prior for the mixture measure here will be a Dirichlet process with the mean distribution as the same as the distribution of the means mu, and the concentration parameter m. If we want, we can also consider this parameter, the concentration parameter m, as unknown and assign a prior for it as well, and estimate with the other parameters. So after the specifications, to estimate this model, we use an MCMC algorithm. To do that, first we're going to introduce a few latent variables which will make this algorithm a little easier. Okay, the first latent variable that we introduce is, we call it U, such that the joint distribution, the joint density of Y, which are our observations in U, is given by this infinite sum. And that works for some decreasing deterministic sequence psi j. So in particular, we use psi j as the explanation of minus gamma times j, where for us we used gamma equal to 0.01. Okay, but the idea of introducing this variable is so that instead of having an infinite sum of mixture in components here, we will have a finite sum. because given u, the number of components is finite, and they will correspond to the indices j such that the psi j's are greater than the parameter u. So with this sum have finite number of terms. It makes it easier for us to implement. The second variable that we introduce is the component indicator d for each observation, which tells us then from which component available the observation came from. So we have now the joint density of y, u, and d given by that. And the joint likelihood function then will be a product of all of that for I varying from 1 to n, which are our observations, okay? So having specified that, the unknown quantities that we need to sample from under that scenario are the mu's, the v's. Remembering the v's, if we have the v's, we have the weights w. The d's that and the u's that are these latent variables that I just introduced. The c, that is the transformation of the mean and the variance of the normal. And the kappa, which is the mode. So we sample from these parameters as such. First, you sample from the u for a uniform distribution. Then you sample from mu via Metropolis Hastings. Sample the c as well via Metropolis Hastings. Then this sampling d we can be done directly because we have the probability mass function. So we can directly sample from there. And finally, the kappa parameters is also sampled via Metropolis Hastings. But surprisingly, that was the parameter that gave us more trouble to sample for. And normally, that's, the location parameter is an easy one to sample from. But in our case, it was the tricky one. So we had to find a very smart proposal to be able to sample from this parameter. So once we finally made it, our test then, to test the model and to test the proposed MCMC algorithm, was to simulate some artificial data sets, and then the idea was that we wanted to predict the densities and then compare the predicted densities to the simulated ones and see how close they were. So firstly, we simulate from a normal with mean 100 and the variance is 100 square, and then we sampled from a gamma with parameters 3 and 10. And we sampled 100 data from each one of those models. Here we have the histograms of the samples. The black line is the real density of the normal and the gamma, and here we have the histograms of the samples that were drawn. Note that that's not the sample of the MCMC, okay? That's just the data that we generated to then test the model. So the algorithm was run for 75,000 iterations. We have a burn-in of 5,000. We recorded the data every 50 iterations. And at the end, we have a sample of size 1,400. Here we have the histograms of the posterior for the mode. For A is the normal sample, and then B for the gamma. And in red, we have the real mode of those densities. So you can see that this parameters was reasonably well estimated. On the normal one, it was well estimated, and the other one reasonably well estimated as well. And finally, this is the predictive distribution under the observations for both models. Again, the black line indicates the true densities, but here those histograms are the ones obtained from the predictive on the MCMC. So we found that there were reasonable results, were satisfied to that, and then the next step was to extend to the multivariate case. Okay. So now, instead of just one observation, we have a vector of a d-dimensional vector. So y is given by y1 until yd. And we work with the same constructions as we worked before. So YL is given by XL over ZL. And the ZLs will be independent, normally distributed. And the difference here is that before we had X as a uniform in the interval 0, 1. And here we are going to introduce the dependence between those observations through a dependence between the axes, which would be this vector x1 to xd. They will be modeled through a Gaussian copula with a correlation matrix sigma. So once again, we can change the mode. So, and then we can write YL as kappa with the new mode for this model, plus XL over ZL. So given X, the mu's, the sigmas, the kappa, etc., we have that the joint density for Y and X given by that product over there. And then, again, as we want to work with Y, we're going to integrate the idea that we need to integrate the copula out. Here's just the multivariate Gaussian copula. And okay, and then our model will be a mixture of those densities that we just seen. Like before, we have the Fy will be a mixture of these densities we found before. The difference here, the problem here is that unlike the univariate case, we are not able to resolve this integral here analytically. So we have to actually sample from the axis. To mimic this problem, and we then went back to the univariate case and did a bridge algorithm, like supposing we cannot integrate the x out. And then we sampled from the axis by rejection sampling, and then we sampled from the other parameters given x. And then we compared the results through this bridge algorithm to the results we got before, and they were pretty much similar. Of course, when we have to sample from the axis, it is a lot slower, but at the end of it works the same. So the predictives and the posteriors look the same. So the advantage then of this algorithm is that we can extend for the multivariate setting. So that's what we did. So for the bivariate setting, because actually that was, which is implemented so far, just for 2 dimensions. Now the unknown quantities are the mu's. Now we have a mu1 and a mu2. I have a C1 and a C2, just for 2 dimensions. And also I have a correlation parameter, which I'm going to call it rho, which is the correlation parameter from the bivariate Gaussian copula that I have to sample from as well. So this parameter is sampled via Metropolis Hastings. And we sample x1 and x2 via rejection sampling and sample from the other parameters the same way as it was done before. So now I'm going to talk about an application to a real data set, which is the Boston housing data. This database comprises 506 cases of 12 variables concerning housing values in the suburbs of Boston. They have been used in many applications, for example, in regression or machine learning. So, but we choose here to work with 2 specific variables, which are nitric oxide concentrations, we call it NOx, and also the weighted distance to 5 Boston employment centers, which we call DIS. So we, doing exploratory analysis, we saw that apparently it looked like there was unimodal densities. The joint density is also unimodal. So here's the histogram of the first variable, the nitric oxide concentrations. The second one is the distance to the employment centers in Boston. Both look unimodal. And the third plot, there is a contour plot of both variables. So what we can see in this contour plot, there is a clear dependence between those 2 variables, but it's not a linear dependence. It's actually quite a weird kind of dependence. So we want to be able to mimic, not mimic, but to find the same shapes and same with our predictions, right? So again, we run the algorithm for 75,000 iterations with a burn-in of 5,000, recorded at every 50 iterations. At the end, we had a sample of 1,400. So here we have then the predictions that we found. And you can see that they are pretty similar to the predictions, not to the real data behavior. Okay, so here's the real data, and here is what we were able to get. Okay, I'm going to skip that part, and I'll go straight to the final remarks because I won't have time to finish. So, so the idea here is that we propose a new class of unimodal densities whose support should include all the unimodal densities on the real line. And our motivation was to do clustering so that each unimodal density would be able to fit perfectly well each one of my clusters. Our objective was also to be able to create such a class that we could extend to the multivariate case. So far we have done up to the bivariate densities, but we want to test codes for higher dimensions, 3, 4. And then in that case, instead of just sampling from rho, we have to sample from a correlation matrix, and that would be basically the difference between the codes. And for future work, we must test this code for higher dimensions, and also do the mixture of the mixtures would be actually to work with a clustering model to be able to use that. Okay. Oh, okay. I just forgot. Some references here if someone is interested, and that's it. Thank you.
Questions for Marina? Questions?
I don't have a microphone.
Should have set it in the back. Can you get more exercise? Yeah, this seems like a very interesting and a new class of models, distributions. But I'm puzzled about where you get your prior distributions from. Let's just go back to the very first example where you have a single normal distribution, and you wrote down some priors for mu and c. I think you took a 0 mean normal prior for mu and some gamma prior for, yeah. So even if there's just one normal distribution, what does the prior on mu mean? Because you see y's, and you've got this distribution, and the parameters mu and c are the parameters of that distribution, but what are they? What is the mean of y in terms of mu and c? What is the mode? The mode is k. So what I'm trying to do is understand how to think about mu and c in prior specification, and how did you do that in your data analysis?
I'm not sure if I understood so well, but the question is, what do mu and c actually represent on this density? Okay, actually the priors, we use what would be conjugate, would be easier to do. Okay, actually, oh no, yeah, you're right, in that case it's not conjugate. Okay, what was usual for a normal? I don't know, yeah, it's a good question, because it wasn't really, yeah, because what I can tell you about the question is that the c here that we maintained fixed, which is the transform mu over sigma square, that works more or less as a variance. But the mu itself, we did some simulations to see, but I don't actually remember so well what it would be. It's not of course, it's not related to the modes or anything. Yeah. Yeah, I could think more about the priors, because maybe you're right about that. I just specify priors that normally specify for mu, and didn't really think if it made sense. Okay.
Any other questions? No? Okay, so let's thank Marina and all the speakers again.